All right, welcome to our second to last section in Chapter 8. We are going to talk first about resonance. All right. So, resonance is when molecules have more than one valid Lewis structure. And we're going to see an example right away. The nitrate ion is that example. It has 24 valence electrons and would need to have a structure like this in order to achieve octets. Okay, so you can see that one of those nitrogen-oxygen bonds is a double bond while the other two are single bonds, right? Because of the way that those valence electrons need to be divvied out. However, if this were the case based on bond lengths, we would observe one bond that's slightly shorter than the others. That nitrogen-oxygen bond that is a double bond would be slightly shorter. But during experiments, we actually have found that all the bonds are the same length and they're the same strength. So that means that while we represent the nitrate ion as having a single bond a single double bond, so one double bond and two single bonds, it's actually a combination of three iterations of this. And it looks like this, okay? So resonance structures will be represented like this, where we have all three opportunities or options represented in these brackets here like this. So that means that the electrons, as they're orbiting nitrogen and as they're orbiting all the oxygen atoms, they won't spend more time closer to this oxygen atom, for example, than this or this oxygen atom, okay? So it's kind of a perfect triune situation where all three nitrogen-oxygen bonds have the same length, and they share those electrons equally, but we have to represent it in terms of these resonance structures. We can't just represent it like this structure up here because that wouldn't give the full picture. So if we're looking at one step further, we could see that it's a combination of the three, and that's called resonance, okay? That's what we would define as resonance. And it's when more than one valid Lewis structure can be written for a particular molecule. So some molecules have only one Lewis structure, and you could change it by rotating at 90 degrees or something like that. But when we're looking at more than one valid Lewis structure, which is what we're getting at, that's called resonance, okay? And we use the average of all those resonance structures to basically understand the molecule. So we know that the true molecule in nature is the average of every resonance structure. It's not just one of them. So these electrons behave in a way that all bonds are the exact same, and this is the best way to represent it, okay? Because we don't want to do like a 1.5 bond or 1 1/3 bond anywhere, so we just represent it with three different Lewis structures that are called resonance structures. And we've also discussed oxidation states a little bit. It was a long time ago, back in first semester, but a more specific way of keeping track of individual charges on atoms, we use formal charge, okay? So this is the difference between the number of valence electrons of an atom on its own, so as you might see it on the periodic table, and the number of valence electrons to the atom in the molecule, all right? So here are a couple of things to note. We need to know the number of valence electrons on the free neutral atom, which has a zero net charge because the number of electrons and the number of protons is the same, okay? So this is the number of valence electrons we would get from the periodic table. And then we need to know the number of valence electrons belonging to the atom in the molecule, okay? So how many are attributed in the actual molecule? So here's a kind of formula for formal charge. Formal charge is equal to the number of valence of electrons on a free atom minus the number of valence of electrons assigned to the atom in the molecule, okay? So to compute the formal charge, we need to assign the electrons in a Lewis structure to specific atoms. Now this might be problematic when you have, say, a single bond or a double bond. You might question which atom gets those electrons. And this is the way we count them, okay? So lone pair electrons belong totally to the atom that they are kind of attached to or that they surround, okay? But shared electrons are divided equally between the two sharing atoms. So when you have that single bond, one electron goes to one atom, the other electron goes to the other, okay? So for an example, we can use sulfate molecule, all right? There are 32 valence electrons total from all four oxygens and the sulfur. Because each atom has 6 lone pairs and shares 2 electrons with sulfur. So you have, has 6 lone pair electrons, right? So 1, 2, 3, 4, 5, 6, and then you have these 2. So that gives oxygen the octet that it needs. However, when we're counting for actual electrons that are attributed to oxygen, we can't just say, oh, it's got 8, right? Because its octet is full, we can't just say that, okay? So instead what we'll do is we'll actually use the we'll find the formal charge by using the formula, and we can show the valence electrons assigned to each oxygen atom, okay? So we have 6 lone pair electrons around the outsides, and then we have 1/2 of that single bond, okay? So that 1/2 times 2, that's this single bond where we've kind of split it and say one of those electrons is attributed to oxygen, the other is attributed to sulfur, okay? And we would do that the same with every one of these sulfur-oxygen bonds as well. So, all, in total, we have oxygen with 7 valence electrons attributed to it, okay? So now we think about what is the formal charge. Well, a free oxygen atom, if you look at the periodic table, it has 6 valence electrons. However, in this sulfate molecule, it has 7 electrons attributed to it. So its formal charge in this molecule is -1. Okay? So you can see that in this diagram as well. So each oxygen atom has a formal charge in sulfate ions as -1. Okay? And the sulfur atom has no lone pairs, and 8 electrons are shared with oxygen atoms, right? So sulfur also has an octet where you have 2, 4, 6, 8, but we're going to obey that same kind of splitting rule of single bonds, or of bonds in general. So we will count sulfur as having 1/2 times 8, which is actually equal to 4, right? So here's how you can look at that. We've got 0 lone pair electrons plus 1/2 times 8, which are the shared electrons. So then the formal charge on sulfur, because it has 6 electrons as a lone atom, as its free atom, you'll take away 4 of those electrons and you'll have a formal charge of 2. So let's think about that for a second as well. If you look up in this top right corner, you can see that this sulfate molecule, the sulfate ion, has a total charge, a net charge of -2. Now, when we think about how many sulfur-oxygen bonds there are 4 of those, and if each of them have a -1 charge, that's a net charge of -1, right? But then when we look at the sulfur's formal charge, it has a +2, -4 plus 2, that gives us -2, which is the ionic charge of this molecule. Just something interesting to note as well. So then there is another possibility for a sulfate Lewis structure though, okay? So the formal charges are listed on the next slide of that, but we could attribute this would also function properly if we have sulfur oxygen, right? Except for, just a quick note, sulfur now would have 2, 4, 6, 8, 10, 12 electrons in its valence shell. So let's look on the next slide and see kind of what that might mean. All right, so for oxygen atoms here with single bonds, here would be the formal charges, 6 minus 7, right? And then for oxygen atoms with double bonds, we have 4 lone electron pairs, and then we've got 4 electrons that are bonded, and those are 6. So the formal charge would be 0, right? And then for the sulfur atom, we would have a formal charge of 0 as well because of all those shared electrons, okay? So formal charges, though, allow us to evaluate Lewis structures. So atoms in a molecule, they try to achieve formal charges as close to 0 as possible. Now let's just look really quickly, and they're talking about the net charge there. So when you add them all up together. So right now we would have 2 with a -1, And then we would have 2 with 0, right? Oops. So our net charge would be -2 still. Okay. So any negative formal charges are expected to reside on the most electronegative atoms. Remember, as you go up and to the right, you get more electronegative as well. So because of this, given our 2-sulfate Lewis structures and formal charges, we would use the resonance structure, structured Lewis structure with double bonds, okay? So this is actually the one that we would use rather than all the single bonds, okay? Because it gets us closer to 0, right? We have more of these bonds that are being shared that have a formal charge of 0. So this is the one that we would determine to use. All right, molecular structure, the VSEPR model, or the valence shell electron pair repulsion model. And it's useful to help us in predicting the geometries of molecules formed from nonmetals. Okay, so this is where we're thinking we've seen the Lewis structure where you see it on a two-dimensional plane, right? Where it looks like these are all right angles, right? But we need to think about the actual geometries of these in 3 dimensions, not just in 2 dimensions. So, in general, the trend is determined by minimizing electron pair repulsions, right? So if you have an electron orbital that has 2 electrons in it, that's going to be very negative, and it's going to want to repel other negative orbitals that have other electrons in them, right? So they'll want to be as far away from each other as possible until another negative orbital repels them as well. So let's look at beryllium chloride, for instance. And since there are 2 pairs of electrons around the beryllium atom, the molecule will have a 180-degree bond angle. Okay, so it would look like this. It would be linear, right? Here's another example. So we could think about this no matter what orientation for beryllium chloride, no matter what orientation it is in, you could rotate it 360 degrees in any direction, and it would still have that 180-degree angle because there are no lone pairs repelling any of those other pieces of negativity. So another example is barium trifluoride with this Lewis structure. So as you can see, the boron atom is actually surrounded by 3 pairs of electrons, which are those bonds here, so 2, 4, 6, and the farthest away that they can be from each other is 120 degrees. So if you think about it 3-dimensionally, it doesn't matter if you go to the side or either side, really, that the biggest angle you can achieve is 120 degrees, okay? So it would be in this triangular shape, sort of. So you have those 120, and even if you tried to rotate that whole thing like 90 degrees horizontally, you would still have 120 degrees, okay? So it's that 120-degree bond angle, because all of these are repelling each other equally, those electron pairs. Now the beryllium chloride molecule with a 180-degree bond angle is said to have a linear structure. That's what we actually classify it as. It is a linear molecule. The beryllium trifluoride molecule has a 120-degree bond angle, and it's called planar. So even though it's 120 degrees between each bond, it's still in a plane, okay? It doesn't go into really 3 dimensions. So it's planar and triangular, and is said to have a trigonal planar structure. So we call that trigonal planar. Methane has this Lewis structure right here, carbon surrounded by 4 hydrogens with single bonds, and it is in a square planar arrangement, which is flat, or if it were in a square planar arrangement, being flat, each pair of electrons would be 90 degrees from the other, right? This right angle right here that we see. However, this is where our 3-dimensional world comes into play, because we're not dealing just with 2 dimensions. This is what it would look like in 2 dimensions, but we have a 3rd dimension that we can work with. So we can find that all 3 can actually achieve an electron pair angle between each of the angles, or between each of the single bonds of 109.5 degrees. So you have one, it's going upward, and then two that are going off to the sides and kind of downward and away from us. Okay, so try to picture this in 3 dimensions, away from us, and then one that's going downward and coming towards us as well. So you get this kind of pyramid shape that we're going at, and we call this a tetrahedral structure. So I know it sounds like you might think, oh, that's going to be planar or pyramidal or something like that, but it's actually just called tetrahedral because we have some other things that we need to account for, like, for example, lone electron pairs that we need to look at. Okay, so when we're dealing with this, here are some steps to apply this model to look at actually what kind of shape it is. So the first thing is to draw the Lewis structure. That's always a good place to start. Look at if it has any single bonds, double bonds, lone electron pairs, etc. Then we'll count the electron pairs and arrange them in a way that minimizes repulsion. Okay, so the pairs are as far apart as possible. So when you're in two-dimensional plane, you can get 120-degree bond separation, or even in a line you can get 180-degree if it's a linear molecule. But this is not always the case. So then we'll determine the positions of the atoms from the way the electron pairs are shared, and then finally determine the name of the molecular structure from the positions of the atoms. Okay, so here are 4 steps that will be really helpful. The other thing too is there are some great examples of all of this in your textbooks, so I'd highly encourage you to follow along and try to complete some of those with your textbook examples. Okay. So these are the steps to predict the structure of ammonia. Here's one example using these steps, right? So 1, we will draw the Lewis structure. Okay, so the Lewis structure looks like this. We look at electrons based on the periodic table. We know that hydrogen has 1 electron per hydrogen molecule. We know that nitrogen has 5 electrons based off of where it is in the periodic table as well. And so then we can put it all together kind of like this, where nitrogen has 1 lone pair and single bonds between each hydrogen and nitrogen. Okay, then we'll count the lone pairs of the electrons and arrange them to minimize repulsions. Okay, so those lone pairs on the top, right? And then we'll determine the positions as well. And finally, we will name the molecular structure. Okay, so these lone pairs, they are very repelling, right? They repel very greatly. So then we'll name the molecular structure, and it's always based on the position of the atoms, not the lone pair. It would be incorrect to say ammonia is tetrahedral like we looked at last time, but because this is a lone pair, we almost ignore it when we're looking at what kind of shape this is, okay? So it looks like it's tetrahedral, just like it was before, but since we don't have an atom up here, we're going to ignore that when we're naming, but it is necessary for looking at the shape of these other 3 atoms, okay? So instead, this is called trigonal pyramidal, okay, because one side is different from the other 3, not tetrahedral, okay? So this is trigonal pyramidal. So this is what it would look like in space, okay? We would not necessarily designate those lone pair electrons. Okay, water now is bent because of its lone pair electrons as well. So if we think about, here's our A is our shape of tetrahedral, right? But then we've got to recognize, okay, we have 2 hydrogens and we have 2 lone pairs of oxygens, right? So we look at all that and we see 1 hydrogen coming towards, or 1 lone pair coming towards us, 1 lone pair going upward and just straight upward, and then 2 hydrogens going away from us and downward a little bit, and that actually creates this bent shape here, okay? Here also are some examples of bond angles, okay? In methane, we get 109.5 degrees. In ammonia, we get 107 degrees. And in water, we get 104.5 degrees between the atoms in our molecule. So we would assume that it would actually be more similar and we would all have 109.5 degree bond angles, but experiments show that the actual degrees are different, right? It's not as spread apart as it is in methane, okay? And now we might wonder, why is that, okay? And one of the things that we can look at is we can look at numbers of lone pairs. From this data, we get that lone pairs require more space than do other pairs of electrons that are in bonds, right? And we might think about that because those electrons, those pairs of electrons, they have nothing positive, right, in them. There's no proton up here or down here, right? However, there are protons and hydrogen in hydrogen, so those have some positivity, but these are all pure, these orbitals here are all pure negativity, and so they actually repel each other and the hydrogen atoms more strongly than would another, say, hydrogen atom, like in methane, right? They repel equally, but in ammonia and water, those bond angles are smaller because these lone pairs here and here repel more powerfully. All right. The following slide shows several different options for the arrangements of electron pairs around an atom. So let's look at that. Here are some examples, right? And ideally in class, we would love to be able to build these. We have some kits that would allow us to build these atoms and their shapes. But far away from one another, we cannot access them. So these are just different shapes and how they might look in 3 dimensions. It's kind of nice to see these pictures on the right side showing us a 3-dimensional kind of picture of what it all is. And the names as well along the left. And that wraps up our lesson for today.